artificial atoms.
Tiny structures, yeah, that essentially act like real atoms.
You mean they mimic their behavior?
Exactly, like having a molecular Lego set. But instead of, building the usual stuff, we're building the future.
The future. That sounds, well, a little dramatic.
Think about it. What if we could design atoms with specific properties? Atoms that, say, could make reactions super efficient or even detect tiny traces of disease.
So not just, like, understanding atoms, but actually engineering them. Where do we even start with that?
Well, a good starting point is quantum dots. Those are tiny particles, just a few nanometers wide.
Oh yeah, quantum dots. I've heard of those. Don't they use them in some TVs?
Yeah, high-definition ones, but they're just the beginning. There's a whole universe of other artificial atoms out there.
Okay, I'm definitely intrigued. What else can we make?
Well, we have what are called superatoms, which are clusters of atoms that, act together as one.
So instead of finding an element on the periodic table, we can just make it. That sounds like alchemy.
It's not magic, but yeah, it's pretty close.
What are some examples?
For instance, imagine a superatom that we designed to act like platinum, which is, a really effective catalyst.
And platinum's expensive, right?
Mm.
So we could use these superatoms to, like, make fuel cells more efficient and cheaper.
Exactly. Or what about a superatom that acts like a noble gas, so normally unreactive, but we design it to catalyze a specific reaction that we need to make, like a life-saving drug.
That's incredible.
And then there's something called single-electron transistor, SET for short.
Okay, a transistor, I know those are important in electronics, but what makes this one special?
Well, a SET is so sensitive that it can actually pick up the movement of a single electron.
Really? A single electron. Isn't that like the smallest unit of charge there is?
It is, and SETs can not only detect them, but they can control the flow, like one by one.
So it's like a tiny gate that lets individual electrons through.
That's crazy. And that level of control gives us all sorts of possibilities. For example, we could have a sensor that can detect a single virus particle based on, just a tiny change in charge.
Wow, a virus detector that sensitive would be amazing.
What else? How about atoms that can actually manipulate light itself?
Manipulate light. Now that sounds like science fiction.
Well, Rydberg atoms have electrons in really high energy orbits, far from the nucleus.
So they're like atoms on a power trip.
That's one way to put it. And it gives them unique properties. They interact strongly with light.
But like, how do we actually use that?
We could use them as tiny optical switches, controlling the flow of light for, say, super fast computing.
Instead of electrical circuits, we'd have light-based ones.
Exactly. Researchers are making a lot of progress. It's a really hot area.
This is mind-blowing. Okay, is there anything else?
Yeah, let's finish with something called a topological insulator.
Topological insulator. I'm lost already.
Imagine a donut.
Okay.
No matter how you, deform it, twist it, the hole stays there,
Yeah.
right? That's the robustness of topology. Okay. Now apply that to electrons flowing on the surface of a material.
So the electrons are like cars, and the surface is a special lane that's always clear.
Exactly. The surface of a topological insulator has this protected pathway for electrons, making them really robust.
But what do we use that for?
They have a lot of potential in, quantum computing, where controlling the flow of electrons is, crucial. Plus, these electron highways basically have no resistance, which means really energy-efficient devices.
So we've got superatoms, single-electron transistors, Rydberg atoms, and topological insulators. What's the big picture here? What makes all of these artificial atoms so interesting?
It's the control that we have. We're not just watching these tiny particles, we're engineering them.
We're not just mimicking nature. We're going beyond it.
That's the exciting part. We're on the verge of a technological revolution driven by these tiny engineered atoms.
It all sounds incredible, but I'm guessing building things at the atomic level is a little tricky.
It definitely requires some pretty sophisticated technology.
I bet. Well, listener, that's just a taste of what artificial atoms are all about.
Stay tuned for part 2 of our deep dive, where we'll actually get into how we build these things.
It's going to be wild.
Welcome back to our deep dive.
So last time, we kind of left off with, how do we actually build these things?
It's true. We're talking about, working at the atomic level.
Right.
And it takes a whole set of techniques to make it happen.
A whole toolkit. What's the first tool we grab?
One of the most important techniques is called molecular beam epitaxy, or MBE.
MBE. Okay, what is that?
Imagine a really high-tech oven, but instead of baking, cookies, it's baking atoms onto a surface.
Baking atoms. Okay, I'm listening.
So basically, inside a vacuum chamber, we heat up sources of specific elements, and that makes them release beams of atoms.
Like we're spraying atoms.
Yeah, kind of. And those beams travel through the vacuum and land on a really carefully prepared surface.
So we're building up material atom by atom.
Exactly, ultra-thin layers.
That sounds like really delicate.
It is. The whole thing happens in an ultra-high vacuum so that there's no contamination.
Wow, 1,000,000,000 times cleaner than a clean room.
Yeah, it's pretty intense.
But it sounds really slow.
It can be time-consuming, but the precision is incredible. We're talking like controlling the thickness of each layer down to a single atom.
Okay, so that's MBE. What other tools are there?
There's another technique called chemical vapor deposition, or CVD.
CVD, is that like MBE? They both seem to deposit material?
With CVD, instead of using beams of atoms, we use a gas mixture.
Okay.
And this gas, it has the elements that we want to deposit, and it flows into a chamber where it reacts with a heated surface.
So the gas reacts and deposits the material.
Exactly. CVD is faster than MBE and more versatile, but it can be less precise.
Gotcha. So MBE for precision, CVD for building structures.
Right.
But how do we shape these structures?
Well, that's where things like lithography come in.
Lithography, isn't that like an old printing technique?
Kinda, but we use light or electrons to create patterns on a surface.
Okay, so what's that like with artificial atoms?
Well, one common technique is electron beam lithography, EBL.
EBL.
In EBL, we use a beam of electrons, kind of like a really, really tiny pen, to draw patterns.
On the surface of the material.
Yeah, and those patterns, they allow us to selectively remove parts of the material and create the structures that we want.
So we can make incredibly small features.
Yeah, just a few nanometers in size.
That's unbelievable.
Yeah.
But all this seems very top-down, like we're forcing the atoms into place.
Right, there are more organic ways of doing it.
Organic.
Well, scientists are looking into something called self-assembly.
Self-assembly? You mean the atoms arrange themselves?
Exactly.
Yeah.
Some materials naturally want to organize themselves into specific patterns. It all has to do with their chemical properties.
So we're giving them instructions and they just build themselves.
That's the idea. We can use tiny particles called colloids, and they have a natural tendency to form these ordered arrays, like a tiny army of robots.
So we're letting the atoms build whatever they want.
Not exactly. We can control things like the temperature, the concentration, and guide the self-assembly process to get the results that we want.
So we set up the environment and let them do their thing.
Right. And by combining self-assembly with those other techniques, we can make incredibly complex structures.
It all sounds very futuristic, but I have to ask, are we playing God here? Is it okay to have this much control over matter?
That's a really important question, and one that we need to think carefully about.
Okay, listeners, that's it for this part of the deep dive. Stay tuned for the final part where we explore the ethical side of artificial atoms.
It's going to get philosophical.
We're back for the final part of our deep dive, and we've covered a lot of ground.
We have, from the science to, how we actually make these things.
But now I think it's time to, step back and think about the big picture, the implications of all this.
Yeah, it's important to remember that with any powerful technology, there comes responsibility.
Right. We can't just get lost in the wow factor.
It's like giving a child a toolbox full of powerful tools.
They might build amazing things, but, well, they could hurt themselves or someone else.
So what are some of the risks with artificial atoms?
Well, one thing that we need to think about is the impact on the environment.
What do you mean?
We're creating new materials, right?
Oh.
And we need to understand how they'll interact with, ecosystems.
So even if they work, they might not be safe.
Exactly. For example, imagine we create a superatom that can, say, break down pollutants in water.
That sounds good.
It does. But what if it has some unintended side effects on, aquatic life?
Oh, I see.
We need to be really careful about that.
Yeah, that makes sense.
And then, there are the social and ethical implications to consider.
Like what?
Well, think about quantum computers. They could totally revolutionize things like medicine and material science.
Right.
But what if only a few people have access to this technology? What if it just makes the gap between the rich and the poor even bigger?
Oh, yeah, I hadn't thought about that.
Like any powerful tool, right? It can be used for good or for bad. So it's not just about the science, it's about society too.
Exactly. And it's not too early to start thinking about these things.
Yeah, better sooner than later.
We need to have these conversations now while the technology is still developing.
Because once it's out there, it's out there.
Right. We have a responsibility to shape this technology in a way that benefits everyone.
It's easy to just focus on the science, but we can't forget about the human side of things.
And, beyond the ethical and practical considerations, there's a philosophical side to this, too.
A philosophical side.
When we start creating artificial atoms, it kind of blurs the lines between, well, the natural and the artificial.
What do you mean?
It makes you think about what it means to be an atom, or even what it means to be human.
It's like something out of science fiction, but it's real.
And it makes you wonder about our place in the universe.
That's deep.
It's about asking those big questions.
Yeah, I think you're right.
To approach these technologies with, a sense of wonder and also a sense of responsibility.
Listener, as we wrap up our deep dive into the world of artificial atoms, keep those thoughts in mind.
We've only just scratched the surface of this field.
It's definitely a journey into the future, and who knows what we'll discover.
But one thing is for sure, it's going to be atomic.
Thanks for joining us, and we'll see you next time for another deep dive.